Welcome to another VMware Code session. My name is Eric Nielsen, and today I'd like to take you through an introduction to Raspberry Pi 4 and sensor programming. I've done this lab a few times at AWS reInvent, at VMworld, and I've updated it with a couple new bits of information for the Raspberry Pi 4. So I thought I would go through that today, as well as introduce you to what I call my home lab. Right, it is upstairs. It's my loft lab. This is a loft. I got a skylight, and I'm up here, and I have a little bit of lab gear that I'll talk about during this session as well. Behind me, I have microscope, soldering iron, heating gun, some other cool things, and I have a slide that talks about what does my home lab look like. And a lot of this lab, you don't need to do Raspberry Pi programming, but it is kind of fun to know what you would need to take sensor messing around at home to the next level. But today I'm just going to talk about Raspberry Pi 4 and sensors. So this is a VMware Code. I'll just do a shout out to VMware Code and say you can go to code.vmware.com and you can sign up for free. If you sign up for free, we send you a Slack invite to our public Slack channels. I think we have maybe 14,000 registered Slack members. I think at any given time, at any given week, we might have 300 or 400 people on discussing. I think we have 80 or 90 categories there. So you can join Code and join us on Slack and talk about provisioning in your data center, all kinds of topics from PowerShell to vRealize automation scripting, to all kinds of topics, including things like sensor management. VMware has sensor management products as well. So we do monthly code talks. I think we do about one a week now. So you can watch VMware Code. You'll get notified. We put you on a mailing list that we send out every month on what talks we're going to be doing throughout the month. So go to code.vmware.com, sign up, and you can engage with all of us. It's a free community. So let's get started with Raspberry Pi 4. I like to always talk about what is a Raspberry Pi. It is a small compute device. If you've never seen them, this is actually a 3. I have several Raspberry Pi 4s at work, but I'm not allowed to go to work. So I'm just showing you a 3, but I have a picture of a 4 here, and I've had many 4s. We ran Kubernetes on Raspberry Pi 4s. You can get the Raspberry Pi 4 kit for maybe $80 on Amazon. Comes with a nice little case and a power supply. You're going to need that kind of stuff. You can get the board for maybe $40. So that's just kind of the price range. It runs an operating system called Raspbian. So Raspbian is a Linux. I think it's a Debian Linux. So it's open source, and you can get it for free, download it. And then on these Raspberry Pi 4s and 3s, they have an SD card slot, a micro SD card slot on the back side of it. You want to get that operating system and basically install the operating system on an SD card. I'll talk a little bit about just go download the operating system. It comes as a downloadable zip. You basically want to format your SD card and then unzip the files on your computer and drag them right over onto the SD card. And that's pretty much what you need to do to load your operating system on an SD card to boot up a Raspberry Pi. Once you put the SD card in, you just power up your Raspberry Pi, and it will go through what I would call a standard Linux boot. It does give you a GUI, which is nice. So if you have an HDMI card on it or a monitor on it, you can, sorry, not card, monitor, you can actually hook your monitor up, boot them, and you have a nice little desktop, which I'm actually running this guy here. Notice I've got my monitor, my keyboard, and I actually have a little OLED display with a VMware Code logo on it. I'll talk a little bit about that in a little bit more time, but it will run a pretty desktop. I don't think I'm capturing the desktop right now, so I won't be able to show it to you, but safe to say that when you boot that guy up, it'll ask you your standard root password, what your network interface needs to be, are you on Wi-Fi? The difference between a 3B and a 3B Plus is that the 3B Plus has Wi-Fi on it. The Raspberry Pi 4s, I think, all have Wi-Fi on them, so you're good to go either way. Now, when you're doing Raspberry Pi stuff, you're going to want to have jumper wires because we have little header pins that you can connect sensors to that we'll be talking about today. You can get your jumper wires. You'll need a 5-volt power supply. And I believe the Raspberry Pi 4 runs on an 18-volt power supply. So it is a bigger power supply that you actually have to buy for that, versus the Raspberry Pi 3s just ran on standard USB 5-volt power. You could plug it into any USB 5-port power, including a power brick. But for Raspberry Pi 4, you'll need to need a power brick for that. And I'll talk a little bit about what the ports are here next. No, I won't. I will come back here and I'll just go around the board. So what is on a Raspberry Pi 4? One, they do have a hardline Ethernet. It is a gigabit Ethernet, so pretty fast, nice little board. The CPU is a new 4-core processor. I think they bumped the CPU cycle gigahertz from 2.1 up to like 2.4. It is a 4-core. I think it has a better bus, IO bus or CPU bus to memory. So it's a little bit faster than just what the gigahertz bump picks you up. So bit faster CPU, but more importantly, it has 4 gig of memory, or you can get 1 gig, 2 gig, or 4 gig. So generally, the Raspberry Pis have been memory constrained if you want to try to use them as a desktop. So with the Raspberry Pi 4 now, it can actually be a desktop because you have 4 gig of memory, and that's enough to run a lot of things. And most video streaming is good on it. There's a 1 or 2 high def 4K things that obviously going to lag, or get a little laggy. But for it's not bad. Plus now they give you 2 micro HDMI ports on the board, so you can actually run dual monitor on this guy versus single monitor. And they have on the Raspberry Pi USB 3 ports. So they have USB 3 versus USB 2. So USB 3 is much faster. You can put another HDMI card on there if you want, dongle. So HDMI 3 runs a lot more devices at high speed. So that's also a nice upgrade. So, but when we're building sensor stuff, there's not a lot of difference. And some people prefer the Raspberry Pi 3s because they use less power, right? And of course, Raspberry has a lot of different options. They have several other boards that use less power, have less memory, have smaller footprint. So you can shop for Raspberry Pis and decide which one is best for you and your project. The nice thing about the 3s is they are 5 volts, right? So you can run them off of any power, and they don't get very hot. The Raspberry Pi 4s, as they bump the CPU up, they get a little bit hotter. They do sell, a lot of the kits sell a little heatsink that I put on my Raspberry Pi 3. Raspberry Pi 4, they make little cases with little fans. So as you get faster and faster CPUs, more memory, you do start to worry about heat. So just understand that. Okay, so let's talk about the pins and what these Raspberry Pis are actually used for. They do a lot of robot projects or various sensor projects around the home automation, where you can actually, hook jumper wires up to this row of pins. And these pins are what makes a Raspberry Pi interesting, because you actually have the ability to hook various pieces of hardware directly onto those pins. And so I'll talk about what those pins actually are. So the first thing any good board would have is what we call a power rail, right? So there are 2 power rails that live on the Raspberry Pi. There's a 5-volt power rail and a 3.3 volt power rail. So understand that 5 volts typically run, bigger things, but a lot of the sensors will run either one. 3.3 volts is a typical voltage for sensors. So you notice in this slide, we have 2 red 5-volt pins, pin 2 and 4. And when I'm looking at my Raspberry Pi, I need to just hold it up. And to the left is the first pin. So pin 1 is the lower left. And then, and I'm looking at the USB ports obviously on the right. So that's the way we orient the board. And I've oriented the board properly when looking at the picture here. So the 2 5 volts are at the very top of the of the pins, pin 2 and 4. And then pin 1 and 17 are 3.3 volts. So those are the two power rails. The two power rails are like somewhere in the neighborhood of a couple amps, right? So an amp and a half, something like that. And these sensors take 20 milliamps. And so if you have an amp and a half, you do the math, that's like 50 or 60 sensors you can drive just from one of those power pins. So you can split the power pins out if you need to. It's just a power rail, and you can hook mini devices up onto that pin if you want to. Same with the 3.3 volts. Plenty of amperage there. So with the Raspberry Pi, you can run probably 100 sensors without running out of power, because these sensors don't use a lot of power. At the same time, they have ground. So the black dots here are ground, and that's just convenient. Notice all the metal parts are also part of that ground rail. So you have power and ground. The ground rail is all interconnected. So it's important to know that, because when you're using the Raspberry Pi like I am outside of a case and I've got it powered up, you got to be careful that when these sensors, they have a power and a ground, you can't arc the ground pin on the sensor. See these little pins on the edge? You won't be able to see it. Those are live pins, and if I touch those onto the metal, that'll be taking power to ground, and it will cause the Raspberry Pi to reboot at the least, and you could burn out your sensor, and you might also burn out the Raspberry Pi. When we would run a lab of 40 people in a lab, and we would run 4 labs a day, we would usually have maybe 3 or 4 Raspberry Pis get burnt out every day. So it is a common occurrence, and sensors also burn out, so be careful. Okay, so that's for power and ground. That's what are on these pins. All the rest of these pins are what we would call GPIO pins, general purpose IO pins. And what these pins allow you to do is send data or send power out and read power, right? I think they run on 3.3 volts. Most of these sensors run on 3.3 volts. And you can send power down the line, or you can read what power is coming up from the line. And then you can do that in time sequence, fast or slow. And that ends up being pulses, which is actually then data. So you can look at a sensor, and a sensor can send pulses down that line, that any of these GPIO pins, and you will be able to read that data. Some sensors that I'll talk about are very simple. Some sensors are much more complicated. And so be aware of that. I'm going to make sure that I get a time check here. I got my phone here, and I'm still good. Okay. So we have a whole hour today, so this should be pretty good. Sometimes I do this whole session in a half an hour, so it's a little bit tricky. But today we have time. So what I would like to talk about is the pins and GPIOs. General purpose IO, all of these pins can be used. Even though they have different color codings, anything that says GPIO on it is a general purpose IO. I can hook a sensor to a general purpose IO pin. But there are special pins that are reserved for various protocols. So the Raspberry Pi supports and has libraries for certain protocols. The most famous protocol is called I2C, and I'll talk about what I2C is later in the slides. But that's a bus protocol, and we have a data line and a clock line. So pin 3 and 5 are reserved for I2C sensors with data and clock. And I2C is a bus protocol, which means much like the universal serial bus or old SCSI buses, or any bus for that matter, you can hang multiple devices off of those 2 lines. And the address will allow me to, I think, put 128 devices hanging off the I2C lines, and I'll talk a little bit about that. There is also a SPI bus line. SPI is very common protocol to talk to sensors. So they have a clock, and CE0 and CE1 is basically an individual line for each sensor, and you can only run 1 sensor per line. So it's a bus, but it's not really a bus. But you have clock and data there, and yeah, so you got that. So that's another set of pins, 19, 21, 23, 24, and 26. Then we have UART, which is a chip-to-chip protocol that people use to send data from one chip to another chip. So if you were gluing chips onto this or wiring chips on, and those chips had UART lines, you could use that those UART pins, pin 8 and 10, to actually talk to other chips. And then they have EEPROM. So EEPROM is the ability to program, store data. So if your project, Little Robot, or whatever you're building has data that you want to store for configuration in the chip, you can put an EEPROM on it. A lot of different devices have EEPROMs that are built in. Ethernet cards, generally the Ethernet chip will have an EEPROM next to it, so that when you configure that Ethernet, the EEPROM gets written, so that every time you reboot that machine, the Ethernet has its own settings already pre-configured for that machine. So that's what EEPROMs are used for when you're building hardware. You won't be doing much of this, or at least I won't be taking you through this today. We will primarily focus on the general GPIO pins and the I2C and SPI buses. All these pins can be just used as individual GPIO pins, and I'll get into that next. So GPIO sensors, what is a GPIO sensor? It's a general purpose IO sensor. As I said, there are I2C and GPIO are the two main sensor protocols that people use, although SPI is also one there. They use 3.3 or 5 volts, depending on the sensor. Some sensors actually have more than one pin on them. And then for a GPIO sensor, all you're doing is looking on that pin and seeing if there's a high voltage or a low voltage on that pin. So this is where it's probably best for me to just kind of introduce you to our sensor kit. This is a smart IoT sensor kit for home automation, and it has a bunch of sensors in it. I think it has 20 some sensors in it, and they're nice little sensors. This is a brand new kit. You can get this kit on Amazon for about $24. So this is a great way to get all your sensors for about 25 bucks. So that's, each sensor is worth about $1. My favorite one that I like to talk about is a motion sensor that they give you. And this is just a nice little sensor, has a little plastic dome on it. You might have seen these in corners of your office building back maybe 10 years ago when they had motion detectors as your security alarm. And all this is a little infrared beam sensor underneath this little white dome, and it sends out a beam, and the little dome has little reflections that cause the beam to bounce out and come back, and it reads how long that beam takes to go, bounce off something, and come back. And then if the time changes on any of the beams, it knows that something moved in the room, because if I have an empty room and this is sending out a beam, none of the time should change because nothing should be moving in the room. But if this time the light takes to come back, it senses that, it'll then just send a high voltage down the line. And you can't see this, but there are only 3 pins here: ground, power, and the one data line that'll hook to your GPIO. And all you're basically using this sensor to do is power it up, and then if it sees movement, it'll send data down that line. The other type of sensor is what we call the I2C sensors. And I2C sensors is a bus protocol. Before I do the I2C, maybe I'll just show you some wires here. We have, let's see if I can get a couple wires off here. I didn't really show this very well. I will do one more wire here. This is my sensor. And on the back of these sensors, it will usually say power or 3.3 V. It'll also say what GND for ground. And so I just have to look at those pins and say, okay, there's VCC, there is ground, and there is your data. So I just want to hook my data. I usually use the yellow line to the data line. I use my black for my ground and red for voltage, VCC. And so that's all I'm going to do to hook up that sensor, is I'm going to hook power, ground, and my data line to the pins. And basically when I power this up, then any motion that happens, it'll send a 3.3 volt down this line. And then you can read that on one of your GPIO pins and just sit in a loop and watch. And that's how that sensor works, is you just look at the sensor every second or so. And if it's on, it means that somebody moved in the room. So that's how we wire these sensors, GPIO directly. The other sensor type that we want to talk about was an I2C sensor. An I2C sensor is a bus protocol sensor. It also takes power. This happens to be a BMP280, which does barometric pressure, temperature, and humidity, right? So I think it's humidity, or is it altitude? Altitude, BMP, barometric pressure. Yeah, this one's barometric pressure, which is altitude, temperature, and barometric pressure. Okay, there you go. Three in one. The point of this sensor is that it has power, ground, but then it has two lines. It has a clock and it has a data line. The clock allows the bus protocol to synchronize when it's sending out data and when it expects data to return. So notice an I2C sensor will have more than just 3 pins. It'll have that extra fourth pin, which ends up being a clock pin. So you'll see that. And then each one of these sensors has an address. The I2C bus will support 128 addresses, 7 bits, which will be specific to the sensor, which is an address, and then the 8th bit being read or write. Now, interestingly, there is an I2C.org site that lists all the sensors and what addresses they run on, because you're wondering, how do they keep track of all the addresses? Well, there's an org that does that so that everybody gets an address, and you can live with your sensor on one of those addresses. This sensor, I have a different sensor. This is an OLED sensor. This OLED sensor has a little resistor on the back that you can unsolder and shift it over to a different pad, and that'll change the address from like 4C, which is hexadecimal, to 4D. And so if you wanted to run 2 displays on, you could move that solder over and set an address. Some of these sensors will run on 1 or 2 addresses. So I talked about this kit. I thought it would be good now just to talk a little about sensors to get you familiar with the sensors before we actually look at some code. Because after all, this is VMware Code. It's not VMware hardware. Although I think it's fun to do both. So first, let's just talk about the sensors. The BMP180 is in this kit. It just does barometric pressure. It doesn't do temp and altitude. It just does barometric pressure, but it is an I2C protocol. Notice it says I2C there. And you can look this up on the web. I just looked all these sensors up on the web, but they're all published out there, and I grabbed them and put them in a table here. So this one's BMP280, and you notice on the pinouts here, VCC, ground, clock, data, and it also says 3.3. So this sensor allows you to run at 3.3 volts or 5 volts. VCC would normally be 5. I've seen these sensors work on both. I've never seen them burn out because you're hooking 5 to 3 or 3 to 5. I've seen these sensors go slower when you run them at 3.3 versus 5 volts. Notice on the right-hand side of the slide, I have the pinouts. Clock, data, ground, and 3.3 volts. So that's it. Now, what does the detect the pressure? It detects pressure and gives you a value back. But there is a library that does the work. You generally just, if it's a complicated sensor like this that's giving you data back versus just on and off, then you'll probably have a library. And there are common libraries for all of these chips. These chips are done by common vendors, like Texas Instruments does one of these chips. And all the little manufacturers of the sensors just use the Texas Instruments chip. So there's only a couple chip vendors and everybody uses it. Therefore, there's a library that works, Python library, C library, and you can just use those libraries to get the data. And I'll show you some code on how we do that in a bit. Another sensor that I like is this is just the humidity and temp sensor. This one doesn't do barometric pressure, it just does temp and humidity. And notice it only has 2 lines. So it is not a GPIO, an I2C sensor, but it does do digital because it is sending digital data down the line. And it will send a temperature and humidity. And I looked at the library to see how they do this, and they pulse it. They pulse it with a clock. And depending on the frequency of the pulses, that's either the data for the temperature or data for the humidity. The library, the Python library or the C library, automatically just sets up objects that you can go call, or functions you can go call to actually just get the temperature and the data. So that is the DHT11, very straightforward to wire up. Again, we just have to put it on any one of the GPIO pins and then power and ground. Carbon monoxide, this is a little more interesting. Notice it does analog and digital out. So it can either give you an analog value or a digital value. And that's nice to have. The Raspberry Pi does not do analog. It only does digital. So you actually have to use the digital out. Yeah, so that's it. Carbon monoxide will give you parts per million. Nice to know. So you can check for in your house for carbon monoxide. And then another simple sensor that's here is just a touch sensor. This is just on a digital GPIO pin. And all you do is run power and ground. When I touch the little pad, it makes a connection and it sends a high voltage down the digital line. And you can just read that to see whether somebody touched the sensor or not. So a standard touch sensor, very easy to use as well. So these are ones that they give you in this home automation kit. And I thought I would just go through a couple more. Okay, so let's see, photo sensor. This is a light sensor. Now, something interesting that you'll see on some of these sensors is a little blue box with a screw on it. And what that's doing is that's setting the sensitivity of the sensor so that if you're light sensing and you want to get whether there was light in the room or not, you can set that how sensitive you want that sensor. And that's a variable capacitor or a variable resistor depending, and that will turn. You put a little screwdriver in that slot and you can turn that to increase or decrease the sensitivity. Again, 5 or 3 volts. This will work on either at the same time, a ground and analog out or digital out. And again, the Raspberry Pi does not take analog data. It only takes digital data. The Arduino actually had an A to D converter on it. It would take analog. What is analog? Analog is just a voltage level, right? 0 volts to 3 volts. And it just gives you a number. It just gives you how much voltage is there. Analog can be very precise because you just get a voltage number and it'll just give you what that number is, versus digital is always just how, like if it's a 4-bit number, then you can only have whatever it is, 96 different combinations of an answer. You can't have, or an 8-bit number would do 256, but an analog will give you 1,000 points between 0 and the voltage. So some of these sensors will give you both analog or digital. The Raspberry Pi would normally convert it to digital so that you could do something with while you're programming, but doesn't have an analog digital. I show you an A to D converter chip on a slide later here. So that's why I'm spending some time on it. Finally, there's a gas sensor, a vibration sensor, getting the sense of how these things work now. They're either 5 volts ground or with digital out that's on a digital GPIO. The vibration sensor just senses if there's vibration, it'll send a high voltage down pin 1. You can set the sensitivity of that vibration sensor at the same time. Carbon monoxide, again, gives you a stepped range for digital or gives you a number in analog. But again, you got to convert your analog to your analog to digital anyway. And then we've talked about my famous infrared motion sensor. Again, it just gives you an on-off depending on if anything moved in the room. All right, perfect. I will move on. So today we do have some code that we're going to talk through that will work on the digital touch. It'll work on the infrared. I'll show you some BMP280 code and some OLED code. And if you want to go get that code, you can go to tinyurl.com/Raspberry Pi sensor code. And you don't have to type all the code in from the slide deck that we have also published on the code website. So this is what we're going to talk about next. And we did these in Python. There are C libraries. Python is a very easy language to use. It's not compiled, so you can just write the code and run it. You don't have to compile it. And there are libraries for Python for every possible sensor out there. So a friendly language. It's object-oriented. It's easy to understand. And yeah, so that's what we're doing. And there's Python libraries for everything. So I thought I'd start with some simple code here to just talk about, hey, how would I use my favorite little, this guy, the motion sensor? Well, I want to first wire it up, and I need to give it ground. I need to give it power, and I need to give it voltage, right? So I put the ground, and I got to look at this and go, okay, I want my red on the first pin there, which is pin 1. I want my output, which is my digital out, on pin 2. And then I want ground on my pin 3. Then I'm going to hook that to my Raspberry Pi. I'm going to grab 5 volts on the first pin there, which is easy to do. I'm not actually going to run this, but you know, that's it. Just put it on there. These little female jumpers. There's the third pin is the ground. Make sure you, so you're not hooking power and ground up wrong. I've never had anything burn out by just hooking GPIO wrong, but if you hook ground and power, if you reverse those, you have a shot of burning out your sensor. And I like to just go grab a GPIO pin, you know, down at the end here. So I have it on pin 39. So I'll just put mine there on pin 39. And that's it. I've wired up a sensor. Now, you can wire your sensors however you want. They make little bus connectors. You can get bus connectors, ribbon cables, or you can just use these little for messing around. And then now this is the Raspberry Pi code that I'm going to talk you through, which is pretty straightforward. First thing I'm going to do is import a Raspberry Pi GPIO library. This library comes with Raspbian OS, so you don't have to install anything, go get anything from the web. It's just there, but you have to import the library into your code. And then we're importing it to an object that we're going to call IO, right? So IO as IO. So when I call things in the IO, I'm actually calling the GPIO library. So we'll see that in the next couple commands here, or lines of code. Import time, we are going to have a clock. We're going to go to sleep, wait in a loop, because I want to go to sleep for some amount of time before I look in the room again. I'm not going to sit and burn my whole entire CPU cycles on just looking in the room. I got other things I want to do. And so that's talking about your frame rate. Simulators, flight simulators have a frame rate, so that when I turn the joystick, I'm flying, and I turn the joystick, you know, you need worst case 1 millisecond frame rate, which is maybe 10 milliseconds. We're, you know, 10 1,000ths of a second. When I go like this, it's going to do this because I feel real. Well, that frame rate is how often you want to go through your loop of code. And you can do a bunch of stuff in that loop, but you always have to get back to the top of your frame rate. So in a security thing, maybe your frame rate would be once every 5 seconds, so that, you know, you're going to come look at that sensor, loop, go to sleep, or do other things, and then come back. So we use the import time library because we're going to go to sleep in our loop. Once I've imported those libraries, I want to use the IO library to set the IO mode to board mode. And board mode means that I'm going to reference the pin numbers, not the GPIO numbers. That's all that does. You have 2 ways to reference things, Raspberry Pi and Python. One is via pin numbers. One is through GPIO. I'm going to set it to pin number because I like pin numbers. I just like looking at the pins and connecting my pins. Then once I've done that, I need to set up pin 40, which is where I think I used pin 40. Yeah, I did. Pin 40 on the where I set up my line in. That's going to be my data line. I put it on pin 40, and I want to tell that pin 40 to be in input mode, which means I'm going to read power on it. I'm not going to write power on it. So understand that that's setting that up so that I can read. So I say IO, which is our object library for the GPIO. And then there's a function called, or a method, I like to call them functions because they're just bits of code that you call inside that library, called io.in, right? And or setup, called setup. And I'm going to pass it in pin 40, tell it IO in, which says input. So that's what's happening there. I've now set that pin 40 to be IO in. I could set it to IO out, and then I could write power to it, write data to it, or turn it from low to high, 0 volts to 3.3 volts. Now I just say if IO input 40, which says if IO input 40. Well, it says go read pin 40, go get the input pin 40. If it's above, I think it is 0.8 volts or some number like that. It's less than a volt, but it's somewhere between 0.4 and 0.8. I forget. It will come back as a high, a 1, and it will say, I've seen movement there, right? So that's it. That's the code. If input on 40, which says if there is an input, which means there is more than 0.5 volts on that line, it will come back as a 1. So anybody that knows if 1, if IO 1, that means it's true. Print I see you. Else, print all quiet, no motion. Go to sleep for a little while. And I think I got rid of the while loop here just because I wanted to save some code. But I would put this in a while loop and it would just go to sleep every second and then go check to see if there's input on pin 40. And that's all this sensor is going to do. Notice this sensor has 2 variable little dials on it. You can't probably see those, but they're orange and they have screwdriver slots. One is for the sensitivity because it is measuring movement in the room. And then the second one is how far out do you want it to look, right? Because light is time. Time is if you're measuring a 1-inch space versus you're measuring a 15-foot room. This will do a 15-foot room. It'll actually do a 20-foot room. So it'll go out 10 feet in any direction. So these are kind of a nice thing. But you do have to set the sensitivity and the distance with those 2 little settings. And I'll tell you a story. When we were doing this at a lab at VMworld, we hooked this up and we hooked it onto our pin 40 and ran it. And at home, it works great. Got it to VMworld, and all we were getting was high. No matter what we did, we covered it, we didn't cover it. Sometimes we get it to go low, but basically it was reporting motion at all times. And it didn't matter whether we set this super sensitive or super far distance, it was just always high. But yet I'd come home and it worked great. We realized after a while that we were actually this little yellow data line was acting as an antenna, and there's so much waves from Wi-Fi hubs that there was so much energy that it was acting as an antenna, and it was driving the voltage up on that line past the 0.5 volts, and it was sending a high, and I was reading a high voltage. Even though there was no sensor data, I could actually unplug it and then read the voltage on the line, and it was coming high because we had so much electromagnetic interference in the room that it acted as an antenna and was pulling that voltage right out of the room. So that's a fun story, just to know that there's a thing called shielded wires. And if you're running a long wire across your garage or whatever you're building, you definitely want to do that. And I will tell one story that I have been telling along the way of a project that a guy did. He actually used this sensor, put it in his garage, and when the garage door opened, he would sense that his garage door opened, and then he did a little OLED display like the display I have, but he actually had a number display, and he put that on the wall, and then he used a sound sensor that measured how the distance between the Raspberry Pi, it sends sound waves out, hits the car, bounces back. As the car drove in, he could sense how far away the car was. He could then say stop when it was time to stop. And many of these projects, you build them and they're a lot of fun to do. But the reality is he could have hung a tennis ball with a string to the glass of it in the windshield. It would do the same thing. But it's a lot more fun to do these type of projects. So they do work. They do work for the size of the garage, but you might want to have shielded depending on how long a line you're running from your sensor. Okay, so that was easy code. That was just a GPIO read on a pin, and away you go. You're good. You're good to go. The next level sensor that I like to spend a little bit of time on is the barometric pressure sensor, and this one is a little more complicated because it grabs multiple data. It actually has a chip on it, right? And the chip is a sensor chip that picks up the barometric pressure, temperature, and altitude. And so temperature, pressure, and altitude. Actually, it's, yeah, okay. So there you go. So this is a more complicated chip. It uses the I2C bus, and that's what's going to be different between this sensor and the previous one, is that it's going to use the bus protocol to talk on those pins, and I have to wire this chip. This sensor is actually a dual bus protocol sensor. It'll do SPI or I2C. Notice it says it on the sensor, and it has the pins for both, and you have to choose which pins you're going to use. We use the I2C sensor. I left code in here. If you wanted to use SPI, you could just wire it to SPI and do the same thing. I have the Python code here, and I just pulled this code off the web. I didn't write this from scratch. There's code examples for every single one of these sensors out there. So know you there. Now, like any bus sensor you're setting up, it runs on an address. So you might want to hook it up and then run an I2C detect command. The Raspbian OS comes with an I2C detect command that you can run. I don't think you have to install a library for it, but you might want to Google that. I know that I have it installed on my OSs, and we do it for the lab machines. And you can then run it. If you've ever ran probe SCSI in the old days, it's the same type of command. It goes out and looks at all the addresses on the bus and then tells you what's there. The BMP 280 runs on address 70, which is hex, and it'll report back. It'll give you a nice little table. I2C detect gives you a table with all the addresses, and where it finds a sensor, it shows it, right? It says, oh, 77 here, or 70 right there. And so you can look at your address table and see what sensors are on there. This comes in handy if you're wiring up a handful of I2C sensors and you want to make sure that you're not conflicting from one or the other. And so that's good to know. The second thing you need to do is you need to get a library, because again, this is a sensor chip. So you're going to need a library. Adafruit is a company that makes libraries. They make sensors. They don't own a whole market. There's a lot of them on Amazon that you can go get different sensors now, not just Adafruit. But the library works with this chip, right? And so you can just go get that library. It's Python. You need to install it. So you need to become root and pip install it with pip sudo pip3. It will actually install the library. Once you, and the command is sudo pip3, and then it wraps install Adafruit circuit python -bmp280, and that will go get it. Or you can just go download it off the web. It's on GitHub. All of these libraries are on GitHub, github.com. You can go search on any library, the chip name, and you'll see it. You can go download it and unzip it, and then just run Python space install, and in the directory it'll actually go. There's an installer.py in the when you unzip it from GitHub. There's an installer script there, and you just run Python space install.py, and it'll go install your library. And I have a director of where it puts all these libraries. At the last slide, I'll show you where it puts the libraries. Python does that. Let's get into the code. Python code, just call it code.py. Again, we import the time library because I would normally go to sleep when I'm sitting in my loop. I import the board library. I'm going to use the board, reference the pin numbers. I have to import a bus IO library. The bus IO library is for talking the bus protocol, and they support, Raspberry Pi has I2C and BMP280. You don't need to download anything. That just comes as part of the Raspbian OS. So, but I need to import that library so that I can set up an I2C bus object. And then I need to import my Adafruit BMP280 library. And those are the things that I'm going to actually import. Now that I've imported it, I want to create an I2C object. Oops. an I2C object, and I call I2C. I just set up I2C. That's going to be my I2C object that talks a bus protocol, and I use the bus IO library and the I2C function or method, and then I pass it in the board.clock and the board.data lines. And board abstracts that out so that it knows what the clock and data line is for the I2C thing, so that the library will know that this is a Raspberry Pi 3, this is the I2C clock and data line, and you don't have to put that number in your code. You could remember that it's pin 3 and 5 and put that in there. So I could have just called, because I'm using the board function, I could have just called busio.i2c and passed it in 3 and 5. That model is just a little cleaner because you're not putting hard coded numbers. So if I took this code to a different Raspberry Pi, it would probably work. But yeah, or I could just put 3 and 5 there. Now that I've done that, I now have a bus object that's going to be talking I2C down to pin 3 and 5. That I2C object now I'm going to pass in to the Adafruit library, saying, hey, Adafruit, when you want to talk to the barometric pressure sensor, just go use I2C, this bus interface. And so I call the Adafruit BMP280 library, the I2C function, and I pass in the I2C object. And now I get a BMP280 object, which is basically just a function that I can use to call and get data from that sensor. And I'm in good shape. I could use the spy code there. I commented that out, hashtags or comments in Python. And I'll just skip ahead down to now. I'm going to set the barometric pressure at sea level to whatever our sea level barometric pressure is, and that normalizes the sensor, so I get an accurate pressure and accurate pressure when I call it. So that's setting that in the BMP280 object. So it'll use that to normalize what it's going to print out for you. So if you're living in Denver, which is a mile high up, your barometric pressure is going to be different, and it should probably say not sea level, but ground level, so that you have a normalized pressure for your ground level. And then now I just sit in a loop while true, print, and it's a float, BMP280.temperature. So I'm just using that object and saying, go get me the temperature. That's all the code you need. And it'll just print out the temperature. It'll print out the pressure, and it'll print out the altitude. Then I go to sleep for 2 seconds. So again, easy to Python code to just go read the sensor, but you're using a library that you downloaded for that sensor versus the motion sensor. You didn't need a library. You're just looking at the pin and seeing whether it has voltage or it doesn't have voltage. When you're using a bus protocol sensor, you have to talk a bus protocol. And you also, because it's usually a more complicated sensor out on the bus, it'll have a chip, which means you're going to have a library that supports that chip. So yeah, that's how that works. And you can see that I've showed you where I wired up the lines, and I'm ignoring these other pins because those are for the SPI connectors, and you can do either one. All right, we're cruising right about on time here. So the last sensor that I want to talk about, and this really isn't a sensor, but this is just kind of fun to have as part of your project. So when I'm running a Raspberry Pi, I can obviously hook an HDMI cable and run a display on my Raspberry Pi if I so choose. But if you are using this as like a project in your garage or on the wall or whatever, you can get various different display options. This one is a 4-digit counter LED counter display. It comes with a Raspberry Pi Python library so that you can just write numbers right to the device, and it'll write numbers. You can write characters to that. I have one that said Merry Christmas, and then I made a second countdown timer that just sat and counted the seconds till Christmas. And then I put that on a battery pack on the Christmas tree, and it just sat with a small Raspberry Pi and counted down. And it's green, so it looked very Christmassy. A counter that ran down, and then on the Christmas morning, it just said "Merry Christmas" because we were at Christmas, which was a lot of fun. So this is one type of display that you can use, big numbers. Another type of display, or they have these little OLED displays, which is 128 pixel by 64 pixel little display that'll print out data. And there's a library that you can do fonts, you can do graphics, you can do lots of different cool things with it. And it acts as a display, and it'll hook to your Raspberry Pi. So if you want to see your data in real time without having a monitor and a keyboard hooked up, you can absolutely put one of these little OLED displays on it. And these little OLED displays cost like maybe $7 on Amazon. You can get them. They're 0.96 inch OLED display. You can just Google it and you'll find many of them on Amazon. And I have one running here where I've actually got the Code logo on it, right? Because it'll do graphics and it'll do bitmap graphics. And so I took a bitmap of the Code logo, and I just used one of the functions to write that image right out to the display, and it works quite well. So this code allows you to actually do some display work, and I thought I would show this. Again, this is also a I2C sensor. It runs on address 3C. And yeah, you can, that's what we're going to do here. We're going to do the same type of code, just to take you through it. I'm going to import time because I like to go to sleep. I didn't need to import the GPIO, the SPY library. I could remove that. I should go through the slide and remove that at some point. The next thing I'm doing is I went and got the Adafruit library for the SSD 1306. So that's what this is. This is a chip that controls a OLED display, 0.96 inch, and the chip is named the SSD 1306. And so if you Google SSD 1306, you'll see all these displays. You can go to GitHub and search on SSD 1306, and you'll see the GitHub library. You can download it and install it. You'll need to do that because we're going to use that library to talk. At the same time, I create an object from PIL. I import image draw, and image font. And PIL is I want to say Python image library, which allows you to manipulate images. And we're going to manipulate images to draw fonts and to draw images. And we want an image palette to be able to do that. So that's what that's doing. You need to bring them in from Python image library to do image manipulation. That's part of Python. It's part of the Raspberry. You don't have to go get that. The only library you need to go get is the Adafruit SSD 1306. Once you have that, I'm going to then create a display. The RST24 says this is how to interface with the pins. That's another way to interface with the pins. There are, I think, 24 I/O pins out here. That's the model type for it. So this is another way to interact with the pins. And then I'm going to make a display object. I'm going to call the Adafruit library the SSD 1306. And that SSD chip will run in 32 by 64 or 64 by 32 mode, or 128 by 64. So basically low res or high res. So you can do that. 128 by 64 is what I'm going to run in. I'm going to run it high res. I have to pass in the pin numbers or the way where the pins would be, the way I'm going to address the pins, and I have to pass in the I2C address, which is 0x3C. The RST24 means this was Raspberry Pi 4. It knows where the I2C pins are, so it's going to use pin 3 and 5. You don't have to specify pin 3 and 5. And then I have to pass in the address. If I had done another OLED and soldered the other one on 3D, you could put 3D there, and then you could run dual-headed display. I've actually done that. I split the jumpers on the I2C. I put soldered the resistor over, and I was in good shape. And that's why I talk about soldering irons and microscopes. I'll talk about a slide at the end here that you can move those little resistors around if you want. You'll need a microscope like the one I have in a slide, and then a soldering iron. And I'll take you through what I have in my lab. right, this code. Pretty straightforward. I initialize my display. I set up my display. The object is called DISP. And then I call begin, which initializes the library. And it sends a bunch of hex codes down to the display because this display is configurable to run in a bunch of different ways. And so that will initialize the display. Nice to know. And you can go read about how you can change those hex codes in libraries to make these displays do different things. But the default way is fine for most of the stuff we're using. Then I need to set I'm going to go get the width and height, which the library will tell me. That's good coding. I know it's 128 by 64 because I call that method. But this is a way to go query it. You can query that. And then I can create a new image by using the image library. I'm going to use a 1-bit image, which is just either on or off, 0 or 1. So it's a 1-bit image. And then I give it the width and height. And now I have an image panel, not the actual display, but a virtual panel that I can draw on. And when I'm done drawing, then I send that drawing down to the display. Right. So that's what I'm doing there. I create a draw object using the draw library because the draw library allows me to give points and say draw a line from point A to point B. So I initialize a draw object. I pass in the image that I'm going to be drawing on. So it gets a little more complicated, but not too bad. Then I can draw things like a rectangle, but I'm going to blank the whole thing. These little OLED displays are interesting in that they remember what they did last. So the app could have been died here. The app isn't running, I think, right now. I don't think this thing's actually even booted. But because it has power, it's still going to show that code logo because it remembers the last thing it did. So I'm drawing a blank circle, fill 00, which says blank the screen. I'm blanking my OLED. So whatever was on it before isn't going to be on there any longer. I do some padding so that I'm not going right up to the edge. Then I'm loading a font. The font for the Python image library allows you to load true type fonts. So I'm going to load a true type font here, and I'm going to use it. So that's my setup to be able to use. Now in a loop that I go to sleep for a second, whatever, I'm going to actually write a little jitter graph, or it'll actually ping the League of Legends server and tell me what the ping time is to a League of Legends server, because the League of Legends puts it up on the corner, but it's so small I can't read it. So I have my Raspberry Pi and I sit and I just constantly ping the League of Legends server so I know what the lag time is. So that's what this little app is trying to do. I actually ripped out the code and just simulated it here. But you can see that I'm drawing a rectangle 00 in my while loop. Every second I go through and I blank the screen. Then I just draw right onto the screen, League of Legends. You can see that. Start time 2 minutes, then a ping, and then what is the ping time? And then this little code here just artificially creates a ping time because I ripped all that out. But if I ran it, it would sit and cycle through some ping times and give me some ping times there, and that would run. I go to sleep for a little while, change the ping time, then I come back and print out the ping time again. So this is nice little code, nice little Python code for you to use these OLED displays. If you want to make a cute little project, this is how you do it. It is an I2C bus. So if I have the BMP280 and the OLED display, you'll see that it has, if you do an I2C detect, you'll see both of those addresses in your little I2C detect table. Okay. Okay, let's see where we want to go back here. Some other stuff. Here's my lab. We did this one already. This was there. This is an extra slide with the BMP280. So I will get to the 8-channel A to D. Remember, I talked about the fact that the Raspberry Pi doesn't do analog. So if you do have an analog voltage, you can use this chip. This chip, actually, the reason I call it out is it comes in the smart home automation kit. They just put a little chip in here somewhere. This one might already be missing. I might have lost it, but it's just a chip. They give you a bunch of connector wires. I don't see the chip. Oh, here it is. Yep. They put a little foam, little foam thing, and it's just a chip there. You can buy a little socket that'll sit in, that'll hook to these little connectors. That might be nice to do. They sell little sockets for like $1 that'll go into. I'm not sure why they didn't give you a socket that this would sit in that you could then hook these female. If you try to hook these female jumpers directly to the pins, they don't fit. They're too loose. So you need to get one of these little sockets. And this is a 16 pin chip, so you need a 16 pin socket. But then all this does is it's a SPI interface, and the right hand side connects to SPI, and then the left hand side, each one of those channels is a place that you can run a voltage in. So channel 0, you can run a sensor voltage into that. Channel 1, channel 2, channel 3, channel 4, each one of those can be a separate sensor, so that you could run 8 sensors into this chip. And then there is a SPI library that will go get, that you can get, called the MCP3008, which this is who make the MCP3008. I want to say it's Texas Instruments, but I'm not sure. I think it's TI. They have a library. It's in Adafruit makes it. Will allow you just to go and do an MCP read on I being 0 through 1, and it'll give you the value, I think it's a 10-bit number, 10-bit binary number that'll tell you what the value was coming in from the sensor. So that's taking an analog voltage and converting it to digital, and here's a library to do it. So if you run into that scenario, now you've seen an analog to digital chip and how it's used and how to wire it, and some code to reference that A to D chip. Finally, my favorite, if you were going to have a lab, here are the kind of things you would want to have in your lab. To be able to solder resistors on and off, change address settings, make a good project. And this is for under $300. These are all active. I got this just about a week ago from doing this session, which this is like June 14th or something like that. Tweezers, you need tweezers. You can get a nice tweezer set for $6 on Amazon. These are all on Amazon mostly. Some of these are from different places. Breadboard is nice if you're just wiring things together. It has a power rail and a ground rail, 2 power and 2 ground rails. That's the blue and red on each side of that. And then little holes that you can connect other wires to. So if you have these components and you just want to wire them up, a breadboard is a super nice thing to have. You don't need to have it because you're mostly going directly, but there are on occasion reasons to put a resistor in line. And if you do, then that's the way to do that. If you are going to solder, get a solder reel with a solder. This is super fine solder. So you want a tip that's super fine. This is not going to be your normal soldering iron. This is going to be stuff that's super fine that allows you to solder super small things that you can't even see without a microscope. And if you look at these sensors that are here, the BMP280, you look at these guys, you can barely see what the resistors are, let alone try to get a fine tip in there, let alone use regular solder. So you want the solder here that I'm listing, and a reel for $20 you can get, it'll last your life, right? And then you have it, and it's very convenient. Same time, you'll want a soldering gun and a heat gun. The soldering tip is great for soldering things. If you want to solder a chip on or off, or even a resistor, take it on or off, the little heat gun, you can dial in the temperature like 350 degrees, and it has a little tips there, and it aims the heat, and it'll basically melt all the pins at once. And you just take your tweezers and peel it right off. And that is super nice. It's super easy. You think it would be super hard to pull off a chip. Well, it is if it's a 4-pin chip. You can't do a soldering gun and heat up all 4 pins. When you move to the next pin, the other one freezes. So you need this little heating gun. Now, this is an all-in-one unit, a heating gun and a soldering iron, micro tip that's replaceable. So if it wears out, has nice little stands for everything. For that one is $94. So that's real. But when you're building stuff, nice to have that. Solder, modern day solder, still has lead. So when you're sitting soldering, you're breathing lead. you can go crazy by the time you're my age, right? So if you've been soldering for 20 years, because you're in your 30s now, and now I'm 58. Breathing soldering lead is a very bad thing for your whole life, and it'll make you go crazy when you get older. They make nice little filters, and you have to get one of these. $29 comes with carbon activated. Basically, you turn it on and it pulls air through it, and the carbon thing catches it, and it keeps it away from your mouth, you breathing it anyway. But then the carbon filter also captures it. So you absolutely, if you're going to be doing any soldering, you need one of these. It's good for your long-term health. So buy one of those, $29. Now, if you're going to be doing interesting stuff with circuit boards, which you can with your little heater, you want a scope. You can use a normal microscope. These are viewing scopes that I would normally look petri dishes, right, to look at cell growth and things like that. But you can actually turn that around, put the heavy part backwards, and then put that around. And I do this. I have another one that's a small one that we use, and we just got one of these and towed around. It works great. So I put a link there, and it will. Let's see. I think I have this on the slide. Where is that? $29, $38. Camera microscope. There it is. It's a link to it, but I don't show the price on the slide, do I? Solder scope. Oh, there it is. No, 105 plus 38. Yeah. So you need the ring light. Without the light, it doesn't light up. I don't know why they don't give you a ring light with the unit, because you absolutely need one. That's just an LED ring, super bright. You need to get one, $38 plus 105. There's a link to both of those on the website. So for under $300, you can have a complete, nice little station that all will fit in a cardboard box about this big. My son does hardware engineering, and he keeps it all in a cardboard box and puts it in the corner. They live in an apartment, and he just brings it out when he needs it. All that'll fit in a standard 1.5 by 1.5 by 1 foot cardboard box. It'll all go in there, maybe 1.5 feet. One of the typical ones, small ones you get at Home Depot box, and everything will fit in there. And when you want to do some projects, you pull it all out, and you can pull out your stuff, and you're in business. So a nice way to do some home fun. And then let's see, we're almost at the top of the hour. I'm already over the hour, so we're going to get done here. So these are some links to the actual, some of the stuff we've talked about. CODE.VMware.com, go check that out. Wavefront blog. If you're interested in doing sensors, we have Wavefront that'll get sensor data. There's a fun project there. Here's some of the Python examples I showed you, the barometric pressure and Raspberry Pi LED blinking microcontroller, some fun projects to do. If you're interested in sensors, this is a nice little kit for $25, but here is a link to top sensors and some tutorials for them. Comes right off the Raspberry Pi website. And home sensors, the home sensor kit. This is a link to the home sensors. You can go get that link there. And I will do I have one more slide, or is that it? That is it. That is it. So code.vmware.com is where the slide deck can be found. I also put this on this front page here. This is the link to that. You can go to blogs.vmware.com 2019-0614. You can go look at this slide deck, as well as how to build a Kubernetes environment as well. So both of these are places that I put these slide decks, and I'll put a newer version up on blogs.vmware.com/code. This deck itself with my lab stuff, you can go get that there. And I hope you get some time to have some fun. I did a session on how to build, use Raspberry Pis for Kubernetes. There's a lot of kind of cool stuff out there to run sensors, even running as a Kubernetes workload. So we did that. Go get some sensors, do some projects. I am Eric and I Pro at Eric and I Pro on Twitter. Tweet me what you've done, what you built. Would love to see some of the projects you guys figure out what to do with. Thanks a lot, and have a great day.